Hey, welcome aboard for our unit 7.1. Today we're taking a look at elements and binary ionic compounds. So it's our my first attempt here at the video notes using Zoom. So welcome aboard. Hopefully this is helpful. Let's get to it. So we're starting a whole new unit today, whole new unit, whole new semester. And this unit is called nomenclature. We are naming a lot of the compounds that we'll be working with this year. And we're starting off 7.1 as we just discussed in the intro there. With elements and binary ionic compounds. Binary means two. So we're working with ionic compounds with just two elements. We'll get to those in a minute. Starting off with elements. So whenever you're asked to name an element, whenever you're given carbon or magnesium, we usually just use the chemical symbol. So again, as examples, if you're given elemental gold, you just write AU. That doesn't save you a whole lot of room. You're still writing two letters as opposed to four, but for longer ones, such as magnesium, it's quite a shortcut just to write Mg. For carbon, just write C. Whenever you have two letters, the first one must be capitalized. The second letter must be lowercase. You don't always have two letters. Carbon, for instance, only has one. But whenever you have two, the first one's capitalized, the second one's lowercase. So this works for just about all the elements. If you're given sodium, you write Na. If you're given potassium, you write K. But there's a handful of elements that are just a little bit different. And these are called the diatomics. So there are 7 elements that always exist as what we call diatomics. So di means two atoms that are always together. They're known as the diatomic 7. Very creative name. And they are H2. So again, you notice the 2 there. That's how we know it's a diatomic. 2 atoms of hydrogen always found together. I can give you 1 atom of carbon. That can happen. I can give you 1 atom of magnesium. I cannot give you 1 atom of hydrogen. It has to come as a pair, the diatomic. Oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Those are the diatomic 7, again, always found in a pair. There's 2 ways you can memorize these. And yes, you're going to have to memorize them, not just for this chapter. Sometimes I give you guys a an element, and you have to tell me whether, what the symbol for it is. If it's not a diatomic 7, you just write the symbol. If it is one of the diatomic 7s, you have to make sure you put one of those little subscript 2s behind it to indicate that it's diatomic. So yes, important for this chapter, but it's also going to be important in later chapters. When we start writing balanced chemical equations, if oxygen is given off as a product, you have to make sure that you write properly O2. Otherwise, you're never going to be able to balance that. You don't know how many atoms of oxygen you have. So very important that you do know and continue to know these diatomic 7s. So one way is when you take a look at the periodic table, the diatomic 7 make a 7 on the periodic table. Now, one of them doesn't fit in. Hydrogen's up here. You got to kind of remember he sticks out back up here. Hydrogen is a diatomic, but otherwise, the other 6 are right here in the shape of a 7 on the periodic table. Another way you can remember is with the name Hofbrinkel. And that's actually why I listed them out the way that I did, the order that I went in. Hofbrinkel. I've never actually heard that name ever before, other than with the diatomic 7, but I can always think of Hofbrinkel. And if it's one of the letters in that name, it's a diatomic. Next up, ions. A little bit of review here. And all atoms are neutrally charged, meaning they have the same number of protons with positive charges as electrons with negative charges. Those positive and negatives cancel out, and you get a neutral charge. When atoms gain or lose electrons, they're known as what we call ions. Ions. Metals. So on the left side of the periodic table, here's our stair-step line. And on the left side of that, metals tend to lose electrons and form positively charged ions, which we call cations. When we name them, we keep the same name as the element. We just add the word ion at the end. As an example, calcium 2 plus, we would just call calcium ion. So that 2 plus, that lets us know we have a positive ion, a cation. The element name stays the same. We just add the word ion at the end. Na plus 1, again, that plus 1 indicates we're working with a cation. The name's going to stay the same. Sodium, and we'll just add the word ion at the end. Nonmetals gain electrons and form what we call negative ions, anions. Anions, so they have more electrons than protons, they're negatively charged. We call them anions. When naming, the rules are a little bit different here. We drop the ending of the name. and we add IDE. So for example, oxygen as an ion, so at -2 lets us know work with an anion. We're going to drop the ending. And this is the oxide ion. Cl -1. And that -1 lets us know we're working with a negatively charged ion, an anion. We're going to drop the ending and call this chloride. Not chlorine now, but chloride. Knowing exactly where to drop the ending, you just got to kind of get used to it. I think the more you work with, the more you practice, the more used to it you're going to get. I will let you know that there are not that many nonmetals. So again, nonmetals are on the right side of the periodic table. Here's the stair-step line. Over here on the right, nonmetals. We don't really have to worry about the noble gases. You can kind of take those off. They don't ionize, not that we're going to work with. So it's really only about these 10 right in here that are ever really going to ionize, and we'll have to add that IDE. So the more you see those 10, the more you'll get comfortable with where to drop off the ending and add the IDE. And it takes practice. You might make a mistake here or there every now and again. Oxygenide instead of oxide, or phosphide, phosphoride. Just a little bit of practice. But the more you see them, the better at it you'll get. All right, again, a little bit of review here before we really get into naming this binary ionics. Oxidation states. Now, the term itself might not be so much a review. You might not remember the term, but you should remember the idea. We did work with these before. I think you'll see it in just a minute. So an oxidation state is the charge an atom is likely to have when it forms an ion. So on your periodic table, and I'd get it out right now, and I would add the oxidation states if you haven't already. Everybody in this first column here, the alkali metals, including hydrogen, even though it's not an alkali metal, they're all going to form +1 charges. That's their oxidation state. So if you're ever working with one of these atoms as an ion, you know that it has or will have a +1 charge. On to the alkaline earth metals, group 2. They all have a +2 oxidation state. It's going to add that right there in your periodic table. If you're ever given something like barium, I say, what's the charge of a barium ion? Just look up and see the +2. We're going to skip over D block for now. We'll come back and look at those guys later. Come over here to group 3A or group 13. Boron and aluminum will form a +3 charge. I'm going to skip over carbon. We don't ionize him very often. You either have to gain or lose 4. That's a lot either direction. So we'll not mess with him. We'll come over here to the nitrogen family. Their oxidation state is -3. They're going to tend to gain 3 electrons. That's their oxidation state. Oxygen and his family, -2. The halides are -1, so these guys all tend to form a -1 charge, and 0 for the noble gases. Again, we're not going to work with them much. They don't tend to gain nor lose electrons. So those are the oxidation states, and they'll be important. We have to think about those as we work to balance our binary ionics, and that's what we're moving into now. So our binary ionic compounds. Again, binary means we're working with two elements. Ionic means that one of them is a metal. So again, a bit of review from last semester, but make sure you're comfortable with this. We're going to have a lot of different sets of rules, and it all depends on being able to determine what you're working with. We have an ionic compound. That means one metal, left side of the periodic table. And one nonmetal. Which is the right side of the periodic table. And again, it's not a perfect half and half. When we say right and left side, we're referring to this stair-step line. The right side is over here, the right of that. So one from each, one from the left, one from the right. You have an ionic compound. Binary means you're only going to have two elements. We'll start by going formula to name. So kind of as we discussed before with our ions, the metal name stays the same. So we start by just naming the metal, no change. And as we mentioned before with our ions, the nonmetal changes its ending to IDE. Take a look at a couple of examples. NaCl, again, first thing we have to do is identify that this is an ionic compound. We have one element from the left, a metal, sodium, and one element from the right, chlorine. So yes, we are working with a binary ionic compound. The metal's name is sodium. That's not going to change. The nonmetal, we drop the ending and add IDE. So sodium chloride. CaBr2. Again, we're working with a metal and a nonmetal. It's a binary ionic compound. Calcium, the name of the metal does not change. Bromide. Bromine drops its ending and adds IDE. So that's going from formula to name. Not terribly difficult. Biggest thing you got to remember, drop the ending of the anion and add IDE. How about the other way? Name to formula. The trick to this is that charges must cancel out to zero. You must get your positives and negatives to equate out to zero. So that's kind of the trick to writing your formulas for an ionic compound, a binary ionic compound. I suggest use crossing over, what we call crossing over. I'll go over what that is in just a second. And then always remember to reduce when applicable. So always reduce. And let's take a look at a couple of examples here. Magnesium sulfide. And this time we're going from the name to the formula. I would start by writing my ion name, magnesium. Got to check my periodic table here. There's magnesium, plus 2 charge. So here's my ion, magnesium 2+. How about sulfide? Hey, that IDE Makes it sound a little weird, but that's sulfur. So there's sulfur, -2 charge. Now you might see how it balances right away, and if you do, that's fine. Sometimes you don't. My suggestion is what I call crossing over. I'm going to bring this 2 here down behind the S, and the 2 here down behind magnesium. I'm going to write this. I'm going to clean it up. Never keep the charges in your compound. Our compound needs to get back to 0, so I don't want to see those charges. So I'm going to rewrite this, Mg2S2. So see how that's a bit cleaner. And then also, we got to remember, reduce. Always reduce. A 2-to-2 ratio can be reduced down to 1-to-1. So the proper way to write magnesium sulfide, MgS, just a 1-to-1 ratio. How about potassium oxide? All right, potassium, let's double check the periodic table here. Here's potassium, +1 charge. So I'll start by writing my ion for potassium, +1. Oxide, and it takes a little getting used to, but that's oxygen as an ion. So oxygen, he's got a -2 charge. Again, the idea is I need to get my charges to cancel out, so I'm going to cross over. You don't really have to write a 1. It's kind of redundant. Having the O there is enough. But what this is telling us is we're going to need 2 of our K plus 1s. That'll give us a total of +2 to cancel out our -2. So 2 +2s will cancel out our 1 -2. I'll clean this up again, rewrite it, K2O. K2O is potassium oxide. Can't reduce that any further. We've got a 1 in there. So that is potassium oxide. Calcium phosphide. Calcium phosphide, again, let's start by writing the ions. Calcium, there he is. Alkaline earth metal, +2 charge. Phosphide, again, looks kind of weird, kind of new to us. P, phosphide's a lot like phosphorus, so there's phosphorus, -3 oxidation state. So we'll have a -3. Getting 2 and 3 to cancel out, +2 and -3 to cancel out can be kind of a trick. So again, this is where crossing over can really help us out. Bring the 3 down here, the 2 down there. It's going to clean that up. I don't want those arrows. I certainly don't want those charges in my final answer. So Ca3, P2. That's calcium phosphide. It's going to take 3 of my +2s. That'll give me a total of +6. And 2 of my -3s. That'll give me a total of -6. So -6 and +6 cancels out to 0. And my formula there, calcium phosphide, Ca3, P2. Apologize in advance here. Today's notes are much longer than they normally will be, so sorry about that. This is the last page here. So transition metals. Transition metals, before we skipped over them. So we did our oxidation states before. So the alkali metals, +1, alkaline earth, +2. We skipped over D block. That's down here. These are most of the transition metals. We skipped over them because they can get a little bit hairy. Let's start off with the ones that aren't so hairy. We just got to memorize. Silver has a +1 charge. Cadmium a +2. And zinc a +2. So those 3 we just got to kind of have to memorize. Again, I'm going to add in my periodic table. Why think too long and hard? When I have this readily available, I'm going to add the +1 to silver. +2 to cadmium, and +2 to zinc. So there we go. Now I can just have that easy reference. Those three are going to have those charges. Here is the fun thing about transition metals. Most of the rest of them most our other common transition metals have multiple oxidation states. For example, copper can be +1 or copper can be +2. So it has multiple oxidation states. Cobalt can be +2 or +3. So you have different ions for a lot of these transition metals. My best advice, use the cheat sheet on the back of your periodic table. Here in the middle left, we have a nice list of all the common transition metals with multiple ionization, not ionization, excuse me, multiple oxidation states. So use the back of your periodic table. It'll be very, very helpful for you. So let's take a look at how we go from formula to name with our binary ionics, including a transition metal. Let's say we have CuCl. Okay, so you're naming it. You recognize, hey, here we've got copper. He's a transition metal. Ugh, that means we got to turn over our periodic table, look at the cheat sheet on the back, and there's two of them. There's copper +1, copper +2. Which one do we have? Kind of have to reverse engineer this one, so to speak. Chlorine, we know that chlorine, chloride, forms a -1 ion. He's a halide. That whole family has a -1 charge. So Cl, -1. Since we only have one chloride and we only have one copper, that means that this copper must have a +1 charge to make sure that they balance out. +1 and -1 will cancel out. All right, very cool. So that means we're working with copper +1. Now what you'll notice is that there's two names. There's a stock name and a classical name. We need to use both. We need to get in the habit of using both. I know it takes you an extra 15 seconds to write both of them down when you're doing your homework, but hey, 3 or 4 problems with an extra 15 seconds, about 2 minutes. You guys are perfectly capable of doing this. So, stock name. So you see our first name, the stock name, we use Roman numerals. And that Roman numeral tells us the charge. We're working with copper +1, we say copper 1. The anion doesn't really change. We're still naming that the same way. So chloride, drop the INE and add IDE. So we have copper 1 chloride, or the other way to name it is called the classical way of naming it. And you're still going to see these names, so we need to become familiar with them, so that's why we use them. Copper 1, classical name, cuprous. So copper 1 chloride and cuprous chloride, same thing, CuCl. As opposed to CuCl2. So a little bit of difference here. And we're still working with Cl, still working with chloride, can have a -1 charge, but here's the deal. Now we've got 2 of him. So we're basically multiplying that whole thing by 2. That's what that 2 behind the Cl tells us. So that means we're going to have a total of 2 negative charges. Copper, we've only got 1 copper, no subscript after him, So that one copper must have positive 2 in order to cancel out the negative 2. So this time we're working with copper 2. So the stock name, again, we got to get in the habit of listing them both. Copper 2. Again, the Roman numeral tells us the charge. The chlorine, he doesn't change, so he's still chloride. So copper 2 chloride. And the classical name, again, we look at the backside here, classical name, cupric. So cupric chloride. All right, that's going from formula to name. How about the other way around? Name to formula. Iron 2 oxide. All right, I'm going to put over here, we're taking notes. So, hey, in the margins here, let's add ourselves a little note. Those Roman numerals specify the charge. So when you see those Roman numerals, you know you're working with iron plus 2. If you want to double check, that's absolutely fine. I've got no problems with that. We can find iron 2, and there he is. Iron 2 has a plus 2 charge. And there's your oxide again. Oxygen has a negative 2 charge. Again, we're going to cross over. Clean it up a little bit, rewrite that as Fe2O2. And then always remember, you have to reduce if you can. A 2-to-2 ratio should be 1-to-1, FeO. That's iron 2 oxide. All right, another example here, ferric sulfide. Ferric might get you a few times. And guys, that's fine. Be patient, slow down. We're in no hurry. You're looking on the front side of the periodic table and like, well, I just don't see ferric. There doesn't seem to be a ferric. Ooh. Well, hey, turn it over. Take a look. There it is. It's a classical name. Ferric is iron 3. Iron with a 3+ charge. And again, it doesn't come to you all the time, all that quick. Just slow down. Take it easy. The more you practice, the more you see it, the better the hang of it you're going to get. Ferric is iron plus 3. Sulfide. Well, let's double check. Sulfide sounds like sulfur. It is just the ion version of it. Negative 2 charge. Again, let's cross over. We got to get that 2 and 3 to cancel out. I think the easiest way to do it is crossing over. Tells me I've got 2 of my plus 3 irons. So that's a total of plus 6. And 3 of my negative 2 sulfides. So that's negative 6, positive 6, negative 6 cancels out. Oops, got the E in there. Ferric sulfide is Fe2S3. And there we go. Can't reduce that any further. It's as far as we can go with that one. So ferric sulfide is going to remain Fe2S3. One more I love throwing out there. He's weird. He's an oddball, but hey, better get used to him in case you ever do see him. Mercury 1 chloride. All right, well, there's that one again. Why do you think I'm throwing him out there because he's weird, I said. Why is he weird? Well, he's got that Roman numeral 1. Just spent the last 5 minutes harping about how that Roman numeral tells you the charge, and look at this. That's a +2. Why did I spend all that time telling you that Roman numeral when there's a +2 charge? Well, here's the thing. Mercury 1 is a diatomic ion. See that little tiny 2 is really easy to miss. It's really small. It's right there, Hg2. So really, Mercury 1 are 2 mercuries stuck together with an overall +2 charge. So each of the mercuries individually has a +1 charge, but they're stuck together. We can't separate them. Don't ever try. That's kind of the trick to Mercury 1. It's Hg2. So here's Mercury 1. Chloride, he's got that -1 charge. We need to cross over. Don't need to write that 1, that's redundant. But guys, we can't change that 2. So I know it looks like I should reduce this. No, don't reduce it. Mercury 1 is Hg2, that 2 belongs. We're not going to change them. Hey, there we go. That was some long notes today. I apologize again in advance, or I guess we're not in advance anymore, but quite a bit of notes today. Most of the notes this semester will not be that long, so don't be turned off by this long video. It shouldn't happen again. Have a good one. We'll see you in the next lesson.